Hello everyone. My name is Naser Ezzati Jivan. I'm from Brock University. Today I'm going to talk about DepGraph. Actually, in this presentation, we are investigating performance problems, unexpected latency problems. Let me give you an example. It might help to understand the problem, the motivation to this research. Let's say you develop a software application, you run lots of tests just to make sure there's no problem, right? And you realize that there's nothing, or if there's some bugs, you fix them, you ship it and deploy it, and it works well. Customer is very happy. But let's say after a couple of weeks, a couple of months, you receive an email saying that, hey, so the software, the service, the program, or whatever works well, but only just let's say, just 1% of the time it runs slow. We don't know why, but it's happening now. So now you want to debug this kind of problem, right? So we are trying to find what's happening in production servers, in production environment, for performance problem. But the problem here is not that we have problem. No, having problem is not problem. The problem is why this is not happening all the time, in 100% of the time. If it was the case, then using maybe a profiler, I don't know, debugger could solve the problem. There's a database bug, there's a code bug, algorithmic bug, you can find them. But the problem here, the latency problem, the performance problem, the slowness happens only in, let's say, 1% of the time. It happens only in very specific situations. We don't know when, we don't know why, but we see it sometimes. All right, so we are trying to figure out, to tackle what's going on, tackle this kind of problem and figure out what's going on exactly in some slow request. All right, and our goal is to find the reason behind, the root cause analysis, not just detecting, but our main focus is on root cause analysis. All right, so there are lots of interesting existing works. They're actually we can categorize them in two different groups: on CPU and off CPU. On CPU is methods that examine usually, let's say, the execution on CPU, the duration that a program runs on CPU, right? There are lots of solutions. Profiler that can give you sort of methods, like a list of methods, like ordered or sorted by their running times. All right, so you can figure out which functions actually contributes the most to the slowness, to the latency. And the problem is it shows the list of functions, but it doesn't tell you why. It doesn't tell you why this function is taking too much time, right? But our problem is not on CPU. If it's just on CPU, it happens all the time. Yes, we can use profiler, but the problem is our problem. The slowness, latency happens only in very rare cases, right? On CPU is great, but it doesn't cover 100% of it. As I said, different profilers or debuggers. We for sure cannot use interactive debuggers for this. We cannot stop the program. We cannot stop the word, because that stopping will impose some new latency problems, or may hide the latency problem. Our latency problem usually happens, let's say, in microsecond scale and nanosecond. So stopping can easily hide those kind of problems. All right. And off CPU approaches, some researchers use critical path analysis. All right. So what is critical path? Actually, critical path actually originates from project management domain, right? What happens? It shows all tasks. It's the longest path, is longest distance. There is an example here, but it's not from project management, it's from system level analysis. So it's the longest distance between the beginning, the start, to the end, right? It shows tasks, maybe threads or people, and how they actually run, how much each of them contribute to the overall execution, to the total execution time, right? So for example, I have an example here. Let's look at this graph, this nice actually critical path. This is actually from Trace Compass, which is open source trace analysis tool. So you see that it's the main thread is Java. We are actually investigating Java. What's happening when we run, let's say, a Java program. So the tool here shows actually that it starts running the main Java thread runs the execution, and then it goes to other threads, other Java thread, and there are some waitings. Let's say there's a waiting here for Xorg thread. There's some other waiting for other threads. Critical path can give you this kind of graph, this kind of analysis, and by manually investigating, by manually analysis, you can figure out what's going on. But there are two main problems. One, let's say you see there is a blocking there. How do you know that this blocking state is specific to this specific execution? How do you know that this is not the case in other similar executions, similar requests, right? This is one problem. So we don't know if this blocking is just for our specific slow request, or is the case, or it's happening in all other requests or similar executions. The second problem, let's say we see that there's a blocking which is specific for our request, but what is the reason behind that? The critical analysis doesn't show you the reason behind it. Right? So we are trying to address this problem in our research. So what we do, it actually shows the overall architecture of our solution. So we use basically it's a dynamic analysis. We use execution trace and only kernel level trace, not user space. We don't touch source code. We don't need source code. Our solution doesn't need source code. It just relies on trace, kernel level trace, system level trace. So use LTNG, Linux Tracing Toolkit Next Generation, is a low overhead, open source and well-maintained tracing tool. We use to trace, but if you enable all kernel events in LTNG, it can impose a good amount of overhead. But here we only enables events that are just enough, good enough for extracting the critical path actually graph. So after that, getting events, we convert them to some state. I'm not going to explain this in detail, but anyhow, what we do critical path analysis. We extract the critical path, but this is not specific to our solution. We're using like mentioned work here, but our solution starts after getting critical path. So what happens there? We aggregate the critical path of one execution. Let's say you have several executions or several requests. So you get critical path for each. You aggregate the critical path of each execution or each request. I will explain what this aggregation means. And then we convert this aggregation to a graph called DepGraph. Example is shown here. But the main part is here. You have several executions, slow, fast, different, right? So let's say we have two groups. For each group, we have several executions. For each execution, we have graphs. So what we do, we merge all graphs of groups together and find a representative graph for that group, right? So we have, for example, two groups or several groups. For each group, we have one representative graph. And then by comparing them, we can figure out what's wrong or what is specific to this group, what is specific to this execution. And that difference, the result of that comparison can help us, can show us what's wrong with this slow request, with this slow execution, right? So that graph actually shown one example here. It's about Apache web request. The route actually shows the thread and how long does it take to service this request. For example, is it just as in microseconds, is it 2 milliseconds? I'm running in a local machine just to show it. So it shows that 90% is actually the time of request, 90% of the execution goes for user space. We don't know what's going on there, what's happening there, because we don't have source code and we don't analyze the source code, right? But 9% goes to system call, which actually in that system call, there is a blocking, there's a wait blocking for something else. I'm not showing the rest here, but I will have use cases, 2 use cases later. So, but you say it's not 100% because we cut all like ages less than 2%, just to show the most important. Anyhow, the time here shows that how long. It shows actually dependency. So it says that Apache thread waiting or blocking because of this guy here, and the time here are a percentage of the overall time. For example, the request takes in total 2 milliseconds, and 90% of that goes in actually to run in user space. Let me show you two use cases. First of all, first one is log contention problem. I have here two web requests. Right. So the one in the left, actually the left side shows the fast request. So it takes 2 milliseconds, 2.8 milliseconds. So it shows that 90% is in user space. We don't know what's going on in user space. 9% system call, whatever. But the one which is fast in right shows actually slow request. It takes like 20 times as long as the first one. So it was 2.8 milliseconds. Now it's 40 milliseconds. Right? We want to see what's going on. So, but comparing these two graphs, so actually we see that there is this box here. This actually rectangle shows the difference, the main difference between these two, and we see that the Apache thread in the second one, in the slow request, is blocked by actually some other Apache threads. See here, for example, the Apache thread here by thread ID is 106.8, actually spending 91% of its time on system call, FCNTL, and that inside that system call, there is a blocking waiting for another thread with another thread ID, and that thread is waiting for somewhere. So we don't expect it. We didn't expect it. Actually, the Apache it's a PHP based program. They never block each other. But what's happening here? Anyhow, the graph here actually shows that there is a dependency. There is an unexpected dependency between Apache threads. So that's because, so we looked at the source code and figure out that there is a PHP shared cache. It's called OP cache. That's actually shared between Apache threads. So they're blocking each other in some specific situation. In some circumstances, they want to write. They all want to write into that cache, and because of that, they block each other. So by increasing the size of that cache, actually we solve the problem. We evaluated our method. The maximum overhead is like 10%. So it's kind of acceptable for this problem. It doesn't impose too much overhead. And in conclusion, actually we actually provide in this research we provide kernel level trace-based system analysis method, dynamic analysis, which actually is able to find to investigate on root causes of performance problems. It's low overhead. It's just 10%. And just two provoking questions. One, kernel level tracing with performance analysis, is that enough? We have used kernel trace. We can figure out, we can tackle some problem, but is that enough for all problems? And can we use this method for live monitoring? Thank you very much. I'm here to take your questions.